persons were there.
Good.
Good. So, okay, so after this meeting, maybe we can have a separate discussion sometime. Okay, good.
Okay.
Okay.
Give me about 1 more week. I'm ready for the final of this phase of the final report. So I can get you all the way up to speed.
Okay. Vinuta Patra, you are welcome. Ex Nalco. Vinuta. Oh, Dr. Chatterjee is here. Oh, I wanted to talk to Dr. Chatterjee sometime. Anyway, later on I will have some discussion with him. You know, Mr. Kakkar, Dr. Chatterjee? Your sound is...
Yeah. Good afternoon.
Yes.
Yeah.
Do you know Mr. Kakkar?
I do not have met him earlier, but I have heard about him.
He is in Canada, no? You had given contact, no?
Okay, okay.
Okay. So anyway, so we will start in another 4 minutes.
Sure.
So there are about 45, 50. Oh, Dr. Amit Gupta. Welcome, Dr. Gupta from IBAAS TLC. So there are 40 people registered for this online lecture. So let us wait.
Good afternoon, Bunita.
Vinuta.
Good afternoon. Good afternoon.
Where are you,
yes.
Vinuta? Where are you at present, Vinuta?
I'm in Bhubaneswar now. I'm already retired from NALCO.
I know.
Working as an independent consultant.
I know. So where are you stationed? Odisha or where are you?
Bhubaneswar only.
Oh, so you could have met us
Odisha.
in the conference. You could have met us in the conference.
Odisha.
So you could have met us in IBAAS conference. Why didn't you come?
Somehow I missed it.
Okay. So please send your new email address and we will contact you for the next conference.
Right. I'll do that.
Okay, Vinuta. Okay. 2 more joined. Very good. 17, 18 persons have joined already. So we will start in another 3 minutes. Das Babu has joined.
Yeah. Good afternoon, Das Babu.
Our Pradeep Chaudhary will also join, I think.
Somebody has joined, it seems.
Gautam Pandey. More than 20. Subhendra Nanda. Gagan Vihari Pandey. Please switch off your mic. Please switch off your sound. Please. Vinod Arora. Please switch off your sound. Please. Hello, ladies and gentlemen. This is online lecture series of IBAAS, and I welcome everybody in this online conference. And today's speaker is the well-known figure in smelting technology, Mr. B.K. Kakkar. Mr. B.K. Kakkar is actually having more than 48 years of experience in smelter. And he is located in Canada. And unfortunately, he told that he will not be able to participate online. He has given his pre-recorded presentation and requested us to jot down all the questions. Maybe on later date, if there are number of questions are there, we will invite him to in this online conference. It is almost 4 o'clock morning in Canada in his time, and he is also traveling. So that's what he requested us to excuse him and carry on this online lecture. And later on, he may contact us and we can organize a separate meeting for questions and answer, a time suitable for him, because it's early morning, 4 o'clock in Canada at present. So whatever is there, now let us start our online presentation. And Mr. B.K. Kakkar is well-known figure in India. He has worked in many organizations like NALCO, and and also he was associated with ALBA. Then he had presented a lot of paper in TMS, IAM, IXOBA, and other conferences. So welcome, Mr. Kakkar, and I will request Priyanka to run his pre-recorded lecture. So we will keep our all phones silent and the pre-recorded presentation will start. Thanks. Over to Priyanka.
Good evening once again. As you see on the screen, the title of my today's presentation is The Modern Trends in Pot Preheating and Startup of High Amperage Cells. So I shall share my own experience and current practices which are used in the smelter these days. Also, you will see in subsequent slides that there are plenty of pictures, because I thought that picture speaks 1,000 words, so I don't need to speak much. So let's get started. So the question comes is, why the high amperage pot line? Why everybody wants to build a 500, 600 kiloamps line? Because the high amperage pots are the cornerstone of modern aluminum smelters and are always preferred due to the economic and operations advantage. So also the higher productivity. So by higher productivity, what I mean is that it's a more output, metal in this case, and with the same amount of input, for example, manpower and other resources, etc. So reduced energy cost per ton. So obviously, when you produce more, the cost per ton of metal reduces. Lower capital investment per ton of metal. The capex is high, but per ton of metal, it is less investment compared to if you build a line of 200 kiloamps. So faster return on the investment. So it's the same reasons, you are producing more, probably you are gaining more, the profit is more, and you can return the bankers faster. Improved process stability and better performance. So that's what you will see more of better pot performance in the subsequent slides, which I'll show you. So these are the few driving forces which are behind building a high amperage pot lines. The next point, which I'll just want to emphasize, and don't take me wrong that I'm endorsing, but it's nothing like that, but I just wanted to share my experience. So the modifications in the anode design, lining improvement, magnetic compensation, and control strategies of DX Plus and DX Ultra Plus technology, where I have worked extensively, results in a highly stable and promising pot performance, and which fits the description I just mentioned above. So I just want to inform you that my today's presentation is divided into two segments. So one is the preheat. Preheat, I'm just focusing on the resistor preheat, and it is not the gas-fired preheat. And second part is the bath-up or the startup. So let's see what are the points or the steps which are followed in the heating. Excuse me. So why do we preheat? What is the objective? Pot preparation for the preheat. What are the steps, or what are the, how do we prepare the pots rather? And raw materials. So what are the raw materials which are used? Mainly the raw materials, as you know, that these are the crush bath, pure crush bath, or maybe the cryolite, graphite, or the petroleum coke, or soda. So let's go to the next step. So the next step after pot is prepared, we energize the pots, we cut in the pots. Some places they use the term energizing, some places cut in, some places they use startup. But actually it is not a startup, basically it's just energizing. So we are not yet started the pot at this stage. And what's the duration of the preheat? What should be the ideal duration? And what should be the rate of preheat? And then once the pot is cut in, we have to monitor the cathode temperature and other parameters, of course. So I already mentioned optimum preheat rate. And what are the challenges involved in the preheat? What are the risks involved? So we'll discuss all this in the subsequent slides. And as I mentioned, the second segment is the startup. So what are the steps we need to follow? Bath-up preparation. So here the bath-up preparation, I don't mean that how to generate bath preparation. So here bath-up preparation means the pot is already preheated. It's just a couple of hours before. How do we prepare to tap the bath? So that's what is the bath-up preparation. We'll see in the next slides. Then comes the bath pouring. So this is also important point that we need to pour the bath in a very gentle manner, and you have to ensure that yes, as soon as the metal comes, we have to stop. But we'll discuss that in the next few slides. Then once the startup or the bath-up is done, what are the post-bath-up jobs which we need to do? So it's post-bath-up operations. And then I have a couple of slides which are for the super high amperage cells. So these are not the today's main focus on this, but I thought just for the information's sake, I thought I must put a couple of slides. This is again the dry startup. I will not discuss anything, although it's very important. Dry startup and early life both are very important. Is a part of the startup, but unfortunately I do not have enough of time, so I will not discuss that. But probably in future, if possible. Definitely there will be a separate subject for the dry startup and the early life. So as the first point, objective of the preheat. So why do we preheat the pot? So uniform heating of the main objective is the uniform heating of the cathode. So what is the uniform heating? By uniform heating, that means cathode temperature should be as even as possible. That means the minimum the gradient. Also, it's not only the cathode preheating, it's the preheating of the lining as well. So that is one of the main objectives. Elimination or elimination or reduction of startup anode effect. So if your pot is very well preheated, probably will eliminate having a first anode effect. That is also sometimes eliminated. Some technologies, some people they prefer to have one first anode effect. To bring cathode block temperature close to 900 degrees centigrade or more. So it's always more is always preferable. The technologies where I worked, we have achieved up to 950, 960 degrees centigrade as well. Then quick stabilization of pot after bath up, low voltage. So this is again, it all depends upon the preheating. So we stabilize the pot faster. So reduction of the risk of bath and metal infiltration. So obviously, if the pot is very well preheated, the chances of developing the cracks are not there at all. So bath and metal cannot infiltrate in the cathode. So elimination of cathode air burn, so hot spots. Sometimes it so happened that temperature touches 1100 degrees centigrade in below some of the anodes, and then it's very risky. We start oxidizing cathode, and so these are some hot spots which are developed. So and protection of the lining, of course, as I mentioned earlier, that yes, it's a lining is also protected if it is very well preheated. So chances of leakage through the lining is not there because it's very well baked. So pot preparation for preheat. So it's a very, very important point here because if a pot is perfectly prepared, its preheating will be very well done, and post-operative bath conditions will be very, very favorable, and it will help. So this particular point, the preparation of the pot for the preheat must be done very carefully. So there is a very extensive checklist before a pot is handed over for the preparation, and this checklist is it's a maybe 45 points are there, and it starts say from collector bar flexible connections to the superstructure hoppers and checking of breaker feeders, the beam movement, etc. So once it is done, it's done by the separate crew actually. It's not, although it comes under the startup team, but it's a separate crew which does that. And then they hand over the pot to the pot preparation teams. So basically under the startup team, you can have many teams as well as required, but a inspection team is generally a dedicated crew. And same thing with the startup preheating crew. That is also a dedicated separate crew is there. So once they clear, yes, this pot is ready for the preheat, we start the preparing the pot. So first and foremost, of course, clean the cathode surface with the vacuum cleaner. This is again very important point. I have seen in some places that people, they just blow the compressed air and clean the cathode and start putting the anodes or start putting the coke bed. But this is not a healthy practice. First thing, that yes, cathode must be cleaned with a commercial vacuum cleaner, which is very powerful and takes away all the foreign particles. If you want, you can blow the air, but after blowing the air, must clean with a vacuum cleaner. So it's important. Using the anode template, then spread the graphite or the resistor coke on the cathode. So the next step, once it is done, so we do the chalk marking, and then there's a template, whether it's a wooden template or aluminum template. So I'll show you the pictures in next few slides, what kind of template it looks like. And then the coke bed is prepared. So, and fix the anodes in the pot using the PTM. So once it is done, once the coke bed is done, then anodes are fixed by the PTM. So earlier days, I remember that these anodes used to be fixed with the PTM hook, and then there used to be one operator, pushing the anodes and fixing. But these days, they just lifted with the anode hoist or the anode extractor and fixed on the top of the resistor bed, the coke bed which is prepared. So anode covering with the thermal insulation. So this is also important point, just to avoid the heat losses. So anodes are covered within the gap between the anodes, two gap. Whatever maybe small is this, so it is covered with the thermal insulation, or the we call it cow wool, or you can say glass wool, or any insulation. So then next is the preheat flexibles. So we fix the preheating flexibles. Of course, before that, the steps. So I already mentioned that yes, it has to be properly insulated. And then the back wall and the side end is loaded with the crush bath and soda. So generally it's a sandwich covering, which is first we put the crush bath. Here the crush bath is a pure bath rather, and then the soda, and on top of that again it's a crush bath. So then installation of the fuse plate, that is the startup fuse, and then the preheat monitoring. So which is, again, as I mentioned, it's one of the very important aspect. So I'll go my next slide. So tap bath, and here it's a resistor coke analysis. So I'll just put these two. So here you can see that alumina is written is less than 8%. It's a very liberal. Normally in the pure tap baths, alumina is around 4 to 5%. And the cryolite which is available is above 80%. So also the fluoride, which is written less than 12%, yes, but generally it is available 8 to 10%. So here the ash content is important, it should be minimum as possible. And of course the electrical resistivity. Soda is standard sodium carbonate, so I have not put any chemical specifications here. So now my next slide is the pot preparation, which I'm continuing. So some steps. You started seeing the picture. So as you see that this is a template, and this template is exactly the size of the anode. I mean, you can imagine how big a anode is there. And these are the square resistor coke bed. So every technology has their own, pattern. So some places they use the square, some places circular, So, and on the right side picture, you could see that the pot is totally prepared. So what does it mean? That means it's ready to put the anodes on top of this coke bed which is prepared. Also, I should mention that in the center channel, generally under the 5 breakers or 4 breakers, generally on the size of 400 to 500 kiloamps, there are 5 breakers. So under the breakers, so the hole is done on the cathode and thermocouples are installed. So just to take the temperature. So let's go to the next screen. This is also pot preparation, but it's a different technology. You could see a different anodes. So I was telling you that yes, the gap between the two anodes is covered with the insulation. So that is what I meant. And you could see that on the back wall, it's kind of a blocked, so that once this back wall is covered with the crush path, nothing goes inside. So it remains there. So this kind of materials, there are plenty of things available. So some people, they use the cardboard. Of course, it generally burns, but hardboard it remains there, it protects. Some places they use the steel. So, but this one is a insulated material, so it remains there. So there is no chance. The steel plates which are used generally are not preferable these days because it gets warped after the heating. So this is a different technology pot which we have seen in the previous slide. So let's see what's there in the next slide. So here you could see that there are some chalk marks on the top of the on the stubs or the pin. Some places it's called pins or the stub. So these chalk marks are done to facilitate the covering of the anodes. So anodes are covered only up to this height and not more. And this is only during the preheating. This doesn't apply for the normal operation. So this is again an important point that it's only for the preheating, because some technologies, they have certain, design that yes, heat losses just to maintain the thermal balances during the preheating. So this is covered, and operator, once he sees, then it's controlled in a better way. He knows that yes, he has to cover the anode only up to this side. On the right side, you could see that yes, its pot is totally prepared after this, and all through. So basically, it's generally it is covered with crushed bath, soda, and again crushed bath. One more thing which is very important, that the 4 corner anodes, so one here on the tap side too, and the duct side too. In some technologies, that on the duct side there is a door. So it's very important, because when you start the pot, so you skim the carbon from both ends. So these 4 corners anodes are very well covered, and also on the deck plate we put some thermal insulations just to avoid the heat losses as much as possible, because we lose a lot of heat from the sides. So let's go to the next slide. You could see that here the coke bed is circular, and as I mentioned, yes, it's a different technology, not that the one which I shown you before. And here, if you could see that these anodes are covered almost full, red up to the pin, which was not the case in the previous slide. And also you could see that this is not a ACM or the anode cover mix. This is the pure crush path, and generally this is pure crush path is used, and this type of arrangement is done for dry startup because after certain period of time, say 44-45 hours, so you could see that yes, crush path is already started melting, and the people, they use the crushed path or the pure bath from top of the anode to put it in the center channel. So that is the purpose. These anodes are covered with pure bath, and not in the anode cover mix, not with the anode cover mix, because anode cover mix, it has about 45% alumina, which is not desirable for the startup, dry startup rather. So I'll go to my next slide. So it's just again a picture. So this is, you see that what is mentioned is achieve high and uniform cathode temperature, airtight cavity preparation. Again, it is, you see that it's covered completely. But you could see that there is enough gap between the yoke and the top of the anode covering. So it is very critical. It has to be, so that air should pass through, just to make sure that yes, these pins are not getting red hot. I'm not very sure whether this is a dry startup arrangement, but I can tell you that in this technology, the temperature they reached about 960 degrees centigrade up to the preheat. So I'll show you the graph in the next technology. As to my next slide. So I was mentioning you before the fuse plate. So what is the fuse plate? Fuse plate is simple, an aluminum plate. There's a hole in between, and its thickness varies depending upon how much is the kiloamps. So if it is higher amperage, the thickness goes a little bit more. So in case of new pot line, when we build the new pot line, so this fuse plate is installed, or fuse plate is welded by the construction team. So, but what happens when your second generation pot or third generation pot, do we still fix this? And if yes, then how? We can't weld on the live pot, 500 kiloamps, and then you can't weld it. So what do we do? So generally, there's a I think it's a used Hilti gun. So there are two kinds of rivets are there. So just we use the Hilti gun to put one rivet here and one rivet here. So contact is not as good as it is welded, but to some extent, yes, contact is there. So it's better to put rather than not putting at all, because when we remove the last wedge, when the last wedge is extracted, it's very important that this fuse plate is there in place so that it reduces the spark which is generated by the last wedge. And that is the main reason that in the generally higher amperage pot lines, this fuse plate is used. I'm sure it is used in even 200 kiloamps pot also. And on the side, this is a general view of the starter. Here you see that startup fuse is fixed near the riser. It's near the riser. So it's a first riser. Some places in the second and third generation pot, they use even the nuts and the bolts. But I do not know whether it is good to do it with the nuts and bolts, but I don't have any comment on that. So I go to my next slide. So here you could see that the pot is prepared, well prepared. So the next is that yes, it is hooded. So it's always hooded preheat. I have never seen any pot which is started, which is preheated without hoods, or which are started without hoods. So you see the flexibles are there. Here one more important point is there that although it was there in the checklist earlier, uh, the startup in charge has to ensure that the duct damper is totally closed. For the gases, it is in the closed positions. So it is 100% closed, but there is always a gap so that in the periphery of the on the damper, so that some gases are always go there. So once the pot is prepared, it is hooded, it is ready for the cut in, or it is ready to energize. So on the right side of the picture, you could see that this yellow structure. So what is this? This is a wedge puller device. So we say it's a wedge puller or wedge extractor device. The best part of it is that all the wedges are extracted within 30 seconds. That means the pot is in circuit within 30 seconds or less than a minute, and not prolonging up to 45 minutes as it happens in some technology, that one wedge is removed and then second is removed and the third is removed. Here the wedges are removed immediately, one by one. So one wedge is removed. Once it is done, the second is removed. Second is done, third is removed. So this way, the whole pot is in circuit within short period of time at full load. It's a full load. So we're not putting any shunts on this pot. So let's go to the next slide. So cutting and energizing the pot. So this is a very, very critical operation. So prior to cutting the pot, we have to ensure that, as I mentioned, the dampers are closed position. Somebody has to re-verify that. So using the wedge puller device, as we seen before, all the short circuit wedges are removed one by one, but not in proper sequential order. So you could remove number 2 first, and you could remove number 6 first, whatever you want to. So it's not that we have to go sequentially. The pot is cut in full load and with utmost care. But what is very important is that since this is a very important operation, energizing the pot, some senior man should always be there. So, and also the power plant is on the standby. So in case of any eventuality, any emergencies which comes, so immediately the guy informed the power plant to take a shutdown or reduce the load, but they're always on touch with on the radio. So it so happens. What can happen? So for example, I'm removing the wedge and one wedge is stuck. If one wedge is struck, what happens? It will start, getting hot because whole load is coming on that. Eventually, what will happen is it will melt, and then there's an open circuit situation. So just to avoid these kind of things, power plant is on standby, and not only that, the maintenance crew is also there. So this is a kind of an important operation, and therefore senior person should always be there when we are cutting the pot. So let's go to the next So it's the monitoring of the preheat. So yes, pot is preheated, but our job is not yet done for the 48 or 50 or 60 hours. So the objective is to have a good current distribution in anodes and acceptable voltage drop between the anode rod and the beam, or rod and the flexibles, because flexibles are connected to the beam, rod to the beam. So uniform current distribution is very, very important, because if some anodes are drawing high or some anodes are drawing low, then you can't expect a good preheat. So these days, some of the vendors, they provide the devices where you can, monitor the current distribution in real time, and operator doesn't need to go and, check the current distribution of each and every anode. Facilities are available, but technology is much advanced these days. So also contact voltage drop. So there is a schedule. There is a periodically somebody has to go and do this operation. Cathode surface temperature. So as we mentioned earlier, during the preparation, thermocouples are installed. So cathode surface temperature, people generally they start taking about after 44 hours because it's picked up later. Because our aim is to have at least 900 and above temperature, so it's not picked up in 20 hours or 30 hours. So my next slide is the higher and the uniform temperature. So it's a very well preheated pot. It's a very, very well preheated pot. I'll show you why. You could see the top line, and it's around 980 degrees centigrade within the center channel. So probably it's a dry starter pot. I don't know, but I'm talking of the preheating. So preheating is very, very perfect. And even if it is we want to pour a liquid bath, 1000 degrees preheated pot, so there is hardly any gradient between the liquid bath and the cathode temperature. So it's very, very good, very ideal. So on the short side, you could see this is the blue line. It's about 800 degrees centigrade. So it's about 150, 170 degree temperature gradient, which is very ideal. So on the short side. And in the middle line, which you see, this is for the, it's on the back wall side. So that is the temperature, which is of course less than the center channel, but above the short side. So if everybody wants to have this kind of, that means he has to start preparing the pot in a perfect way. It's very simple. If you clean the cathode with the compressed air or with the broom, we don't get these kind of results. So abnormalities during preheat. So what can happen? So uneven current distribution, yes. So what happened then? If it is uneven current distribution, yes, cathode will not be preheated properly. Yes. What else can happen? So hot spot below some anodes, temperature might reach 1100 degrees centigrade, as I mentioned before. And again, it's not desirable. Insufficient preheat temperature, so temperature will not be uniform. So we cannot, if preheating is not done, then we cannot bath up the pot. Red stubs are red pins, so because some anodes are drawing high, so it could cause all this. Anode burn off. This is a typical case of poor anode sealing, poor quality of anodes, and of course, poor quality of preparation of the pot. Probably the contact is not very good. So it's possible during preheat, although it's rare, but during preheat, I have seen anode burn off, not only in the bathtub. Higher low rate of heating. So if it is very high, that also is not desirable, and if it is very low, that is also not desirable. So it should be ideal rate of preheat, which is considered 15 to 20 degree. 15 to 18 degree is very ideal. Again, it depends upon technology to technologies. How do they maintain the heat balance during the preheat? So for graphitized preheat, average rate of 15 degrees centigrade is considered to be good. Short set temperature not picking up properly, as high amperage pots are designed to dissipate heat. Yes, that is true, but still the gradient should not be very high. So that is why you have seen that I mentioned it, that on the short side we try to put insulation on the deck plate, and even on the four corner anodes we put insulation. These challenges require advanced preheating strategies such as computational fluid dynamics, CFD, for heat distribution, automated control system, and robust safety protocol. So it's very important. So again, it's a design. So how well the pot is designed. So this kind of, I mean, these abnormalities, these are some of the abnormalities, not all. I cannot mention all, but yes, if a cathode is very well prepared, anode stems are very well grinded, the beam is grinded, then these problems are eliminated. I don't say 100%, but yes, to some extent. Common problems during preheat and bathtub. You have seen that I mentioned it, red pin or red stuff. So this is again during preheat, and you could see on the right side that if you could see that this is a clad that is welding between aluminum rod and the yoke. So it gets heated up. Sometimes it gets red hot. So the chances are that yes, if we don't address this problem, then it might drop. Clad may fail. So the rod is separate and the node is fallen off. It's a burn off. So just as a precautions, when this bath-up happens, the people, they have to go around, check each and everything is normal. Of course, it's every technology, they have their own procedures and all. But yes, if it is properly done, these kind of things are avoided. If anode is very well sealed, if there is no problem with the initial anode which is fixed, maybe initially there is a crack or minor crack or something like that in the transition joint, then these chances are very high that yes, we may have problem during the bathtub or even during the preheat. So we come to the next part, that is the part startup or the bathtub. So bathtub stages. So these are the bathtub stages. So bathtub preparation, it's again not generating the bath, it's preparing the bath for the pot bathtub, and post bathtub operation. Now before bathtub the pot, what should we do? Of course, these are some of the steps which are very, basic and fundamentals, and all of you know about it, but I thought that yes, I'll just mention it. We tighten the anode clamps, anode marking reference with the chalk line, remove the flexibles, and remove thermal insulation blankets. So These are the things which, any startup or any bath team, they know about it. These are the important things which we need to do before we pour the bath. So I just put some pictures here. So anode clamping and flexibles removal. So you see that anodes are here tightened. The clamps are tightened, and once the clamps are tightened, the flexibles are removed. So let's go to the next slide, and let's see the bath pouring step. So here, let's see how do we pour bath. So predetermined quantity of the bath, 13, 14 tons, maybe 15 tons. Again, it depends upon what kiloamps what is this and which technology, because it varies from technology to technology, the requirement. Some people they pour 14 tons, some people 15 tons, some people they pour 13 ton and 2 ton later. So it all depends. But in general, 13 to 14 ton of liquid bath is poured in a very controlled manner, gentle manner. So it's not that we pour very fast and not aware that yes, maybe some metal is coming at the end. So we have to be very, very careful during the bath pouring. So ideal temperature of the bath should be above 970 to 980 degrees centigrade. This is ideal, but generally, if it is 1000 degrees, still it's better. So raise the anode beam while maintaining all anodes immersed in molten bath. So once the bath is poured, not completely, but partly, and somebody, as I mentioned earlier, there is a duct side door. So the guy ensured that yes, the bath which is coming anodes it, at least it is half immersed in the bath, and then he gives an indication to the guy who is on the tap side. Yes, it is. Then he starts raising the anodes. So maintain about 45 to 48 centimeter bath height, depending upon the cathode cavity volume which is available. So in the beginning, because there is no metal, so we have enough of cavity available, and also there's a lot of absorption in the initial days of the cathode. So this is the target, which is 45 to 48 centimeter. Generally, if it is 55 centimeter cavity is available, we keep this because the volume will go a little bit high, because once the crushed bath starts melting and if you have anode effects. So, excuse me. This is once it is done, so, and some technologies providers, they advise that we put some alumina dumps just to avoid instant anode effects. But using the tap crush bath, which is about 4 to 5% alumina, we can always avoid this. So some people, they don't prefer to even charging these dumps alumina. Pot voltage is maintained around 10 volts after the bathtub, and 9 to 10 volts. And normally we declare the anode effect at 8 volts. That is the threshold. But during the bathtub, this for the first shift, even at 10 volts, we don't declare the anode effect, because this is the requirement. We need to maintain so much of voltage because we need to heat up the pot. In some technologies, 3 to 4 anodes predetermined are raised about a centimeter after the bathtub. So again, it's a very controversial point. You see that as soon as the bathtub is done, they know, because the pot is so long and anode beam is so long. So they say that probably in the middle, in the center, because of the low total structure. So anodes are there are 40 anodes or 36 anodes or whatever it is. In the middle, there is a possibility that anodic plane is not uniform. So some places they raise 3 to 4 anodes by a centimeter just to maintain the proper anodic plane. Although the current distribution, when they check, we don't see anything. So again, as I mentioned, that yes, it's a practice. Some places they follow, and there is no problem in that. There's no issue if you raise a 1 centimeter anode. After 8 hours, the current distribution, you will not see anything in that. Even during that shift, there's nothing wrong, nothing happens. So what's the next point? A gas stack dumper is open completely. So earlier I said that during the preheat, it was closed. Now it is open completely. What I mean completely is that yes, of course, gas balancing has to be done, but to whatever the limit is there, the mark is there, so we have to open up to that. This is just a picture which shows that yes, bath is being tapped for the startup pot. Now, how do we pour this? This is a huge ladle. It's about 14 ton, as I mentioned, 14 ton liquid bath. So what do? We use the startup tilter to pour the bath in one go. We don't, rather than, in some places, rather than pouring 2 ton, it's not possible for such a big pot. So we use the startup tilter. So I'll show you the pictures. So this is the startup tilters, as you see. Oh, this one is a startup tilter. So this is a bath crucible. The bath is being poured. Now, this startup tilter is some places I think they use the electrical, energy to operate this ladle. I mean, for the startup tilter, the cylinders are actuated by the electric motor. Some places, pneumatic motor, where they don't allow any electricity to be there in the pot line, like it requires 400 volts. And I have seen pneumatic motor also, it works very well. So when we are pouring bath, as I was mentioning you, when we are pouring bath and you are almost done, you have to ensure that there is no metal goes with that. That is why it is very important that we pour the bath very gently. Also, sometimes it happens that there is a chunk of bath which comes on that, and if you are not very careful, this chunk of bath it blocks, or maybe the bath will splash. So there is a risk of the people around working around here. So the guy who is operating this startup filter must focus his eyes on the bath pouring. So it is a startup control sheet which every technology provider recommends. So whether it's a Peshni, Hydro, or EGA, everyone they uses. I have not seen this kind of startup sheet in Gami, but probably it's introduced now. I don't know. So this, I have some. I don't know whether you can zoom it and see the data clearly. But one thing which is very remarkable is that pot is almost normal after 2 weeks. If you see, you could see that the days and the dates are mentioned here, and here the parameters are there. Main parameters are here, but here the values are there. You could see that yellow, that's between 9 to 14 days it is mentioned. We are running around 4.09 volts, which is which is fantastic. That means what it speaks? It speaks that yes, guys, you had a perfect preheat, you had a very good bath up, and the results are here. So normally it's for the graphitized pots, it's about 1 month period. The pot is totally back to normal. But here we could see that parameters are within 2 weeks. The pot looks like normal, which is fantastic. It's a very encouraging results. If startup team sees that yes, this is happening, that means the job which they are doing is really fantastic. So it's a matter of pride for the startup team and of course the operation team that these kind of results are there. So post bath up activities. So again, it's a very important. Generally, we use very less quantity of the graphitized, resistor coke, which is mixed with graphite. So not much of a carbon is generated. So after the startup filter is removed, the carbon dust skimming we need to do from both sides, both duct side and the tap side. Soda addition, which is done as per the recommendation. So we have to keep monitoring the voltage and the noise level. So that means to ensure that if little bit noise is there, current distribution we have to check every 2 hours after the bath up for the next 4 shifts. So again, it's a practice. This practice varies from technology to technology. So it's very healthy practice if we measure the current distribution regularly. And carbon skimming, so continuous, all that we don't generate much carbon, but not to forget that anodes are made up of carbon, so carbon is always generated. So we keep skimming for at least 4 shifts. And once the metal is poured, which is generally 18 to 24 hours, after 18 to 24 hours, then the redressing is done, pot redressing, because the anodic plane is changed and you raise the beam. And so a lot of crush bath from the side goes down. So I've already mentioned this 18 to 24 hours. In modern technologies, voltage of the pot is adjusted automatically while pouring metal. So earlier days, yes, we used to adjust the voltage by manually raising the beam and all. But once now, if metal is ready to be poured, so we just press the metal pouring button. There is a separate command for that, and then you start pouring, and the voltage is adjusted automatically. So whether the beam has to go down or beam has to go up, it's done automatically. You will be surprised that yes, beam has to go down. Yes, if it's required, but it doesn't go down for a larger period, just to adjust 0.01 volt or 0.001 volt or something like that. Or it stops at one place and then wait till the metal is poured. But definitely it has a feature that yes, it goes down for certain period of time up to certain limit. So it doesn't go down much. So as I said, pot redressing to be done after the metal pouring. If metal pouring is done at the end of the shift, for example, so it is done in the next shift. But this is a sequence very important. If we don't do, then we'll see that anode starts burning, and this pot will be basically a donor pot. So it is better to do it after the metal addition. This pot will be donor pot for the next bathtub pot. So it's just, you could see that this is a metal, so not the bath. So it's just a picture for the information sake. So it's now I was mentioning earlier that what are the super high amperage pots? So basically, super high amperage pots are the pots which are running between 550 to 660 kiloamps. And not many countries they have 550 to 660 kiloamps pots. Let's see which are the countries they have. So there are 4 super high amperage technologies. So let's go. What are the advantages of this? So it's of course lower capex, faster return on construction cost, high productivity and lower operating cost per ton of metal. Basically, the advantages are the same which I mentioned earlier. Low specific energy consumption, technical studies of MHD, thermoelectric. MHD is, magneto hydrodynamics. Basically, it controls the movement of the metal, especially the vertical component. And thermoelectric and mechanical modeling indicate it is possible to operate the pre-baked cells even at 1000 kiloamps. So that means sky is the limit. So we'll see after a few years, maybe we're having 1000 kiloamps pot. So super high amperage pots. So let's see what is there. What are the challenges? A major challenge is managing the MHD. It's a vertical component of the metal movement. Higher heat input due to high current. It must be offset by the heat dissipation from the sides. So it's a challenge how to dissipate the lining design, cathode surface and top of the anode. So basically you are putting more heat, more energy, the heat has to escape. So it becomes a challenge while designing. So less bath volume is available for the kiloamps for dissolving alumina because it's a lot of amperage, so not enough bath volume. So super high amperage pre-baked cell technologies in operation at worldwide aluminum smelters. Let's see which are the smelters running the super high amperage cells. So here you could see that the cell technology SY600, it is the SAMI. It's a Chinese technology. You are all aware of it. Any UI 600, it's again a Chinese. One is AP60 running in Jonker in Canada, and RA550, it's the Rusal technology. Now you will be surprised, of course not surprised, but it's strange that everything is happening in China. You see that they are running the pots at 660 kiloamps, 660, and they're running 3 lines. You could see 3 lines, and 600 kiloamps, 3 lines. AP60, still 38 pots. Now they're going for expansion, but still, I think they will start soon about 90 odd pots. Expansion is almost done, as I read just a couple of weeks back. And RA550, so when these results were published, it had only 16 pots. 8 pots. Only 8 pots. These are the experimental pots. But you'll be surprised that out of all these technologies, that RF550, they are showing very encouraging results. 94.5 current efficiencies. So voltage is extremely low. Energy consumption is very low. But again, you see that when these results were published, there were only 8 pots. So these are the experimental or the pilot pots. So where the control and supervision is very high. So these kind of results are, evident. But running the line, big lines, and then they are showing 3.85 volts. 3.85 volts. Energy is also very low, 12.205 and 12,166 megawatt hour per ton. So what it shows is that yes, Chinese are much ahead in this game. Chinese are much ahead. Also, Peshni, basically they were the pioneer when they started it, but I think China overtook them. They are 94.6. Yes, it's a good current efficiency. The voltage is very high. So is the energy, specific energy. So it's a very important to have a low energy, low voltage. So that way, what we see is the RF550 pots as of now, what we know are the good ones. So that's all. I think for this slide. So I conclude my presentation here, and generally this is the most interesting part of the whole presentation when we interact with the audience and ask question and answers. But I apologize that I won't be able to do it due to the time difference. However, you can send me your questions to IBAAS, and I'll make sure that I reply you back at the earliest. Once again, I thank you all for attending this presentation and highly appreciate it. My email address is bkkakkar@carpalex.ca. Thank you once again.
An excellent presentation. This is an excellent presentation, and it's more than 1 hour. And I'm pleased to see that about 45 persons have joined, and they are continuously there in this meeting. So unfortunately, it is early morning, and he's traveling, Mr. Kakkar, and he has excused us that he will not be able to present. But if there are a lot of questions, can request him and find a suitable time to answer those queries and questions. So please send your questions to us, info@ibaas.info, at our IBAAS address, and our office will compile all these questions and send directly to Mr. B.K. Kakkar. So please let us know if you have any other suggestion. You are all welcome. Dr. Chatterjee, any suggestion?
No suggestion. It was a very good presentation, and everybody must have enjoyed it. Very much fundamental and very practical.
Very practical. Excellent presentation. Mr. Arora, yeah, thanks. Mr. Arora or anybody wants to give any comment is welcome. Kurt, any comment?
Excellent presentation. That was really good.
Okay.
Learned a lot.
Okay. Mr. Behra?
Yeah, it was a good presentation. It was from his experience of last 46 years in this field.
Yes.
From very old, like 87 time, 1987, he is doing same job. It was good. We will send our queries and get. Okay. Many thanks.
Okay. Anybody wants to talk or convey his message? Okay. Thanks to everybody, and we will come back with another lecture next month. On the last Friday of each month, we organize this thing. And if any of you are interested to make presentation, please contact IBAAS office.
Thank you. Thank you very much.
Thank you. Thank you. Thanks, everybody.
Thank you very much. Thanks.
Thank you.
Thank you, Dr. Nate.
Thanks, Binuta.